Okay, so I've made a little bit more progress on the automation, and my next step was to refine the rescue missions, which were pretty good. We were approaching on main engines, which is the LV909s. It meant that as we got close, we had to spin it around and stop with the engine. And I was ending up, 50 meters, 20 meters, that kind of range, which is good. But I thought, eventually I'm going to want to use RCS thrusters to do a docking. So I wanted to do a rescue mission where I used RCS to bring myself into a very close distance. In fact, I'm going to go in and just make a last minute change to make that 5 meters instead of 10. So we are going to be very close. Hold on while I fix the scripting here. And yes, the final approach here, I am hard coding with the name 5M. Okay, so we go back to here. So what I want to do is I'm going to start the rescue mission going in the background because it takes a while to get there. And in the foreground over here on my code editor, I'm going to go over really quick the tricks that you need to do to be able to switch from using the normal cooked control, which is lock steering and lock throttle, to actually using RCS to match a given velocity or a given position. There were a couple of things I had to work out along the way, and they're really simple if you know about them, and they're not too complicated if you know where to look for them, but they had me scratching my head when I first hit them. So let's get this guy flying so he'll be ready to do the maneuver when we get there. I am going to go rescue Matzer, who's in a fairly inclined orbit, so he will be exercising a bunch of our old rescue code, which we already know works. We've already gone over. So there we go. That will just take that over in the background. Let me back away so it's not too loud. In fact, let's switch to a map view. I'm going to set her on Kerbin. Make sure Matzer is still targeted there. And now we can look at the code. So the rescue mission itself does its normal search using Lambert for a neat transfer, and then starts the transfer, and then it repeats the Lambert search in a restricted way, looking for the best time to do a correction. Remember, the Lambert solution says, I am here, you are there, and I want to get from here to there in a specific amount of time. And it gives you the velocities. It doesn't care what your orbits are. So if you're already on your way, what you can do is you can say, look at various places between, along my future orbit between where I am now and when I am now and when I get there, and look at each one and what is my delta V that I need to be able to get to where the target is at the end of the time. So real easy stuff. So we're going to do that. I believe that's unchanged from before. We do when we're done, we place a maneuver node at the end of the transfer maneuver. So the Lambert solution said we have an ending velocity and an ending location, ending time. Well, knowing the time and the velocity, we can look at our velocity there and set a node. So RDV node here plants that maneuver node. So we'll end up with a maneuver node on the target vessel, on the target vessel's orbit. Once we've done this burn, we will be matched with the target as closely as we can based on executing maneuver nodes. So we may be within 10 meters, we may be 500 meters away. Depends on how these go. Precision isn't everything at this stage. The next thing I did was I took my existing rescue script, which uses the main engine to get close, and said, well, make it approach so that we are within some range and within some speed match and terminate. It used to be it just kept going until I hit a board. So RDV near gets us near enough, and the idea is I want to be near enough that it is acceptable to use RCS. because I'm going to limit my approach speed in RCS. That way, if you're approaching too fast, you're not going to be able to slow down. And RCS is kind of finicky. So what I wanted to do was have that approach speed limit, which means that if we're far away, let's say if we're approaching at 2 meters per second and we're starting out 200 meters away, well, that's going to take a couple of minutes. I'm willing to wait that, but I'm not willing to wait for a 10-kilometer stretch at 1 meter per second. So we do the near, we do the rescue, which will get us down to 5 meters and will hold us there. And again, now we're back to the usual hit abort to return. So now let's take a look at the rendezvous RCS 5 meter. Basically, we have the normal boilerplate at the top of my phases that says if I'm boarding, continue onward, deal with time warps. In this case, I am canceling any time warp that's there. And then it's basically handing the whole problem off to a module in the control area. So I actually match this position down into the control logic. So CTRL used to be you'd hand it a delta V and it would execute as best it could to match that delta V. And as time goes by, you reduce the delta V vector, it reduces the thrust, and so on. So CTRL now has grown some RCS capabilities like matching a velocity. Well, thrusting until the velocity passed is 0. And now we have thrust until the offset passed is 0. So control RCS-DX says target position minus the vector from me toward the target with length 1 times 10. So this will go straight towards the target and stop 10 meters before it gets there if RCS-DX does its job. So now let's look at the control script. We're not getting into any of the real tricks here. This is all just normal stuff. The thing that's passed in is a function delegate usually. I have a function eval that says if it's a delegate, call it, otherwise just return it. So we could pass in a delegate, or we could just pass in a value. And that's what eval does. Without eval, I would say dxdf, left paren, right paren. Then this is just a normal proportional control. I want to pick a velocity. I want to say, in order to eliminate this position error, I want to have a certain specific velocity, and that velocity is the position error divided by 5. So this is a gain of 0.2, or a frequency of a period of 5 seconds. So yeah, the idea is that we want to have very low accelerations. We'll see elsewhere that we actually can compute the acceleration that our RCS can do, and perhaps this dx over 5 is something that should be based on our achievable accelerations. The other thing we want to do is, no matter how fast, if we're a long ways away, just taking the linear thing, let's say, oh, I want to come in, I'm 200 meters away, so I want to come in at 40 meters per second. Well, I don't want to go 40 meters per second, because that means I have to accelerate to 40 meters per second, then decelerate from 40 meters per second. That's 80 meters per second of delta V I'm dragging out of my RCS tags. What I prefer to do instead is have a speed limit. So I accelerate to the speed limit, and then I coast, and then I decelerate. So if my speed limit is, say, 2 meters per second, I accelerate to 2 meters per second, and then I decelerate 2 meters per second. So that's 4 meters per second of delta V out of my RCS tanks. RCS tanks tend to be limited, so that's good. So there's our linear. There we are going to cap how fast we want to move. Then we say, well, how fast is the ship moving in orbit? How fast is the target moving in orbit? Figure out our relative velocity. And here's our error. So our error term is what we have minus what we want minus what we have. And we pass that whole thing as a function delegate to this CTRL RCS DV. So this is control with RCS for this delta V. So this will apply RCS to drive its parameter to 0. So let's take a look at that. This is a little bigger because this is where we start getting into the tricks of the trade. So first of all, what is my available thrust? when you look at each RCS part, it has an available thrust that it can hit. Now in the background, you'll notice we have prepared our transfer. So let's make that a little more visible while we're looking at the code. So a thruster, I'm using the 5-way orthogonal thrusters, which means each thruster can basically push north, south, east, west, and up for some direction. So there's, of the 6 orthogonal directions, there's one direction it can't thrust, and that's the way where it'd be pushing the flames into the rocket. There's also, you can do the default horn, which is only 4 jets, but they're kind of tilted, so you still get all the degrees of freedom. I went to 5-way orthogonal because I'm weird like that. But this does mean that if I just add up the available thrust from all of our RCS jets, that's going to overstate what I can actually accomplish. So I'm going to derate that. We'll see later what I do with the sum. Here, oh, there it is. So basically I say, assume that over all of my RCS jets, I can get 50% of that thrust in any given direction. And yeah, it's conservative. What this means is that when we use this gain to set our thrust, our RCS command, we're going to get more force than we planned. And that's okay. This is an error controller as long as it isn't too hideously large amount of force. And the fact is that the force we're going to get is going to grow slowly over time as we use fuel. We should be okay. Turns out in practice we are okay. So RCS translation gain is how much thrust do we get from commanding 1 as the translation unit. So the command that we are sending, let's skip down here a little bit. What we're using is the raw control. So we have a translation vector we can set. And that translation vector is not in ship raw coordinates. All the calculations we've been doing so far are all in the coordinate frame that's ship raw. Ship control translation wants it in starboard, upward, and prograde relative to the ship's orientation. So, and a magnitude of 1 says, burn it at 1. So what we have to do is when we're calculating here, so we've got our delta V, we calculate our change in the acceleration we want. This is all normal proportional control stuff. We've done it several times now. There's our acceleration, multiply by the mass to get the force. We multiply it by a gain to get the desired the desired force in that we want to use. Then we rotate it. And this is the first trick, is that to rotate it from this coordinate frame that's in ship raw to the coordinate frame that the thruster wants, you need to rotate it by your facing. And facing directions can be used to rotate vectors and change basis vectors. So we want a change of basis from ship raw to facing. And the way you do that is you take the facing colon inverse and you multiply it by your vector. I'm just going to say, trust me on this one. If you said facing times a vector, it would take that vector which was represented in the facing coordinate system, starboard, up, forward, and it would rotate it back into the normal plane, into the coordinate frame we are used to. Then we look at its direction. We're going to need its direction in a moment, and its magnitude. So, second trick. So first trick was rotating the vector into the coordinate system that it uses by pre-multiplying by the inverse of the facing direction. There's trick 1. Trick 2 is that KSP enforces a 5% dead zone. I'm not sure whether it's total or per bell. Okay. But it's a 5% dead zone, so if you command less than 5%, you get 0. So what I want to do is, if we only need a little bit of thrust, we want to overdo the thrust. We want to bump it up to get some thrust, and then we'll kill it, and it'll kind of jitter back and forth, and it'll get us the change we need sooner than we wanted it, but we'll cut it out. So first of all, if our magnitude is small, we're done. Neutralize controls. If our magnitude is we think maybe in the dead zone, then set the translation to the proper direction for 10% throttle. I'm using 10% here because if that 5% dead zone is a per bell thing, and I said 5%, any bell not completely lined up would go to 0. So by using 10%, that means any bell that is less than 60 degrees off from the desired area will get some burn. So that should make it so that we're good. Oh, and we're actually doing it. We're actually doing the approach now. Let's watch this. So you see we are slowing down, slowing down, slowing down, and we're still burning. You can hear it burning. Puffs of smoke went away first, and now it's bip, bip, bip. And if we didn't match velocity, we would continue to move. This makes this physical system behave like a PI controller, PI error controller. And the physical location is the equivalent of the integrator. So if we get too close or we get too far, we're going to bip our RCS just a little bit to get there. So now we have approached, and it's holding at 9.1 meters from the wreckage. And the velocity, if I can look up here at rendezvous information, our relative velocity is 6.23 millimeters per second. So we are essentially still. So what else did I want to look at here before I do the final bit of the rescue? So if we are very, very close, we neutralize controls. So that's where we are right now. We've neutralized controls. Coming in, you heard it going bip, bip, bip. That was this triggering off. So we needed a very little bit of thrust. So we gave it 10%, which is going to overcorrect, and we'll drive our velocity down to where we need 0. And then we move a little bit more, and the thrust needed creeps back up until it bips it back down. Further out on the way in, you notice the RCS starting to shut down. That's this area here where we're doing linear. Whoops, that's this bit down here. So we're saying, okay, well, we need 50%, so we're going to command 50%, and that worked. And then way out, when we were accelerating to our maximum speed, I didn't highlight that as we came in. We basically thrust with a transit vector of 1. So if this was lined up with a bell, it was going to be going full speed. That's great. So we ended up accelerating to 2 meters per second, coasting, and then slowing down and coming to a stop right there. It did take a while. Now, my little message up here, approaching to 10 meters, please be patient. I should probably have that say something different when you're just parked there. So we are ready to go. I am going to switch over to this guy. Now, the autopilot may crash because we no longer have a target. So if that particular thing requires the KSP target to be set, then it's going to have some problems. That's okay. We will just reboot the system and continue. And I will make a note to fix that in the code later. Okay, so you probably heard the RCS jets kick off there. As I kicked away from the pod, it started moving. And of course, my rescue vessel is going to maintain its position relative to the pod. Now this means I only have to go about 10 meters, which is really good because I'm actually not very good at EVA. I have to take it really slow. So we grab. Little RCS jets kicking in to restabilize us because we did kick the spacecraft a little bit there. And now I'm going to board. And you heard it go bleep. And if we look at the console, KOS here, we see that indeed RCS DX wanted target position. So I need to harden my code a little bit to handle temporarily having no target, because now we're back to having a target. It was only that instance as we were boarding where for a moment we didn't have a target set. But we can reboot, and now we're back to the rescue phase and we're holding. And I can hit abort. And now we are back to the stock standard termination of the rescue mission, where we burn retrograde until our periapsis is within the atmosphere somewhere, and do aero braking passes and land. And that is the rescue of Matzer Kerman from his 2.7 million meter altitude orbit that's inclined at some horrible inclination, like 10-15 degrees or something. I've been working on some other things, but they're not ready to show yet. I have almost got automated the moon stuff, so you can intercept MUN. I can set up a Lambert search and do a transfer to MUN. Okay, and that will plan it to intersect the middle of MUN, ignoring MUN's gravity field, and that's great. That has me transiting into MUN's SOI and then dropping down. And we can take that and manipulate it a little bit. What I want to do, though, is on my automation, I've already got a start on this. You take that orbit, you say, well, if you delay the burn and increase the prograde a little bit, so you're going to end up going out in front of MUN, okay, and you increase the prograde a little bit so that you can then, instead of just being barely caught by it, you're now clearly in front of it. You do that right, you can get MUN to catch up with you and give you a free return trajectory as Apollo used. So you go around the back retrograde, you lose a little bit of your orbital energy around Kerbin, and you end up coming back in a Kerbin orbit that has a periapsis lower than where you started. So this says we're headed that way, and if we lost all control, lost all fuel, lost all engines, our orbit would bring us back to the atmosphere where we could then land. So same thing as Apollo. Second thing to automate there is starting from that orbit, do a little bit of hill climbing, so that instead of getting a free return, we tune it so that our MUN periapsis, or our paramun, is at some reasonable altitude, say 50 kilometers, and set up our mission to get there and circularize. And then once we've orbited a few times, kick ourselves back out. So math isn't done on this yet. I'm still tinkering around with it, trying to get the proper layout of it so that we can optimize it properly and have everything come out as it should. And I'm trying to work out the math for how to do the return leg from an arbitrary MUN orbit. But it's not too hard, it's just fiddly. If I insist on it being either a retrograde or prograde, mostly equatorial MUN orbit, that simplifies the problem quite a bit. Anyway, close on that. Close enough to talk about it, not close enough to show it. So we are... Yeah, the rest of this is bog standard. Don't really need to stream it. I'm going to call this a stream, and the next stream, I hope, will be the stream where we do a flyby of MUN to get more science. So in this one, I've spent my existing science on the RCS and on docking ports. There's the other thing I want to do. I want to do the MUN flyby, and I want to work on an auto docker. So I got docking ports and had to revise all of my code that dealt with targets to handle what if the target is a docking port instead of a vessel or a body, because docking ports are not orbitables. Oops. So anyway, there's that. So there's our two things that are coming up, which is the MUN missions and the docking missions. Those are going to be kind of exciting. So I will see you when I see you.